So today we're going to be looking at solving equations of motion in contextual examples. So we're going to be looking at a free-stage question here, and I'll just read it out. We have a train that moves away from a station and is accelerating uniformly for 30 seconds over a distance of 225 meters. It continues with the speed it acquires for another 135 seconds, then the driver applies the brakes and the train comes to rest with uniform retardation. And that retardation takes 10 seconds. So what we need to do is we need to calculate the distance between the two stations. So, whoa, there's a lot of things going on in that problem, and we're going to need to be able to calculate quite a bit. So, first off, probably the best thing to be able to do is to be able to draw a picture. So we have a train. It doesn't have to be the world's greatest picture, but we just need to get an idea of what's going on. And in the first bit, it travels 225 meters, and it has uniform acceleration, and it's obviously starting from rest. And that takes it 30 seconds. Then what happens is it travels at the speed it has acquired, so it is not accelerating, but it is traveling at the speed it has acquired for another 135 seconds. And we don't know distance, and basically we only know time there. And then what happens is it brakes to the next station for 10 seconds uniformly with the speed that it had before. So wow, there's quite a bit in there. So what the first thing I would do is I would write out the known values. We know that the initial velocity is 0 meters per second. We know that the final velocity is unknown. And we know the acceleration is also unknown, that the first distance we are looking at is 225 meters, and the time is 30 seconds. So what we're looking at here is we're looking at 225 meters being the first distance, so it's always good to keep a little tally here, because distance is the overall thing that we want to look at. So, what I want to know is what the final velocity is, because obviously it's going to travel at that speed for that distance, and I'm also going to want to know what acceleration is from that. So we can't deduce acceleration unless we have final velocity, because of course acceleration is going to be Vf take Vi over t, and we'd have two unknowns. So we need to be able to calculate final velocity first. So, how do we do this? Well, we could try this formula, Vf squared take Vi squared equals 2as, but then again, we don't know what acceleration is, and we don't know what Vf is, so unfortunately we're going to have to cross this one out. It's just about getting an idea of what formula to use. So if we have S now, we could try doing one of the S ones, because we know that that's 225 out the front. And we know the initial velocity, or the Vi, because that's basically equal to 0. And then time, we do know time, because that's 30 seconds. And then plus half, that's fine, because we know that's a constant. A, we don't know acceleration, but we do know time, so we only have one unknown value there, and it's one of the ones that we need to calculate. So, what we have here is we have 0 lots of t, so 0 lots of 30 in this case, plus half a t squared. And we can simplify the first bit. We can just cut it out completely, because that cancels down to 0, because 30 times by 0 is of course 0. So we're left with half acceleration 30 squared. So therefore 225 equals half acceleration 900. So let me go on to a new page, because things are getting a bit crowded, but I hope you understand what I've just done there. I've crossed out 30 and 0, because they equal 0, and I've just gone 30 squared is 900. I got that because basically we have 30 and 30, and 3 times 3 is 9, then we have the 2 zeros to get 900. Really quick way to multiply. So we end up being left with this. 900 obviously being the S value that we got from the distance before. So, half a 900. Well, what do we do if we have half 900? We have 450. So 225 equals 450 times by the acceleration. So obviously A is going to be less than 450. Now it turns out in this example that 450 divided by 225 is actually 2. Or should I say, no, sorry, 0.5. Oh no, wait, no, sorry, it is 2. My mistake. It means that acceleration is going to be 0.5 because as that's divided by 2, as that equals 2 from the division process, we know that this must be obviously the opposite, which is half. And you're probably thinking, well, how do we know that that is the opposite? Well, we can just calculate it again. Because we see that that's 2 there, we know that obviously, okay, hang on, if that's 450 and that's 225 and we need that to equal that, then we're basically bringing the times 2 that would be over here to make 450 over to the other side. And when you do this, this is a neat little trick here that works for multiplication. If it's on the numerator, you bring it into the denominator. So it's basically 450 over 2, but we write it as a half, just for simplicity purposes. But that basically means that acceleration equals half a meter every second squared, because acceleration is meters per second, or 0.5 meters per second squared. Okay, so now that we've calculated that, we can calculate velocity final. And there are a few ways we can do this, but I reckon the neatest way is to go Vf squared take Vi squared equals 2as, which is another equation of motion. So velocity final equals x squared, and then we have take 0 squared, and then we have equals 2as. So from this we can basically get x squared, and then we can just take that away because we're not taking anything from it. So we get x squared equals 2 lots of the acceleration, which is 0.5, distance, which is 22.5. So now what we do is we just simplify the right-hand side. So we have 2 lots of half 225, and they cancel out. It's pretty much the exact same thing that happened over here with the 2 and half when we move it to the other side. They're basically the same thing. 2 lots of a half is 1. Think about it, we have 0.5 and we times it by 2, we're going to have 1, because 2 halves make a whole. So we basically have velocity final squared, or x squared as I showed before, either way, equals 225. So therefore velocity final is going to be equal to the square root of 225, because we just inverse the operation by bringing it to the other side of the bracket. And so we get velocity final equals 15 meters per second, because if you know what 15 squared is, then it's easy to go the other way around. So that's our final velocity. And that will be important for deducing the next stage, where we have to calculate how fast the train is going, because it's travelling at that constant speed for a given time period. So, with the speed acquired, which is 15 meters per second, or should I say it's now becoming the V average, technically, the average velocity, it's travelling for 135 seconds, and basically we just need to be able to calculate distance from this. So acceleration, in case we need it, is obviously going to be 0, because it's travelling at that constant speed. So now, what we do is we work out an equation of motion based on this. And we want to work out distance, of course, because we want our overall distance to be added up, because we're keeping a little tally over here. So, I'm going to go and do this next part in the second video, because this is going to have to be 2 parts, because it's quite a large question. But leave any questions or comments on what I've done so far. I know I've sort of had to rush it a bit, and I couldn't quite be as thorough with some of the explanations, but just watch the second part, and if you have any questions, let me know on the video, and I'll continue on then.